Geometric sequences and arithmetic sequences are a type of recurrence relation. And a recurrence relation is a rule that defines a term based on the previous term. So we can say that the term a of n, right? So a of n, remember we use that variable index. So we can say the term a of n is equal to, and in this case, what is it? It's 4 times the previous one, right? So this term is 4 times 12, the previous term. So what we do is we can say it is 4 times the previous term. And how do we say the previous term when we're using variable notation for the index? A previous term would be n minus 1. That's the adjacent term, right? The one just previous. So this says that we can describe the current term is equal to 4 times the previous term, right? Now, that works in all cases except the first case. What do we do in the first case, right? So that worked for the second one, we were able to compute that. The third one, we were able to compute that. The fourth one, and indefinitely, we can continue to compute that. Except, how did we get this initial term? Like, we can't use this to compute that initial term because we don't have an a n minus 1. That initial term, there's no previous term to do it. So in this case, for it to be completely defined, part of the definition has to tell us what that first term is. Now remember that the index of the first term depends on the initial index. So in some cases that might be 1, in some cases it might be 0, but whatever it is, that would be the initial term, or the initial index. So here it's using the initial index 1 to tell us what that very initial term is. So here it says a of 1 is equal to 3. That gives us the first one, which we can't compute. And then after that, we can compute all of them. So this is the definition for a of 1. This is the definition for all the others. And the way we say for all of the others is we go for n, and we say it's everything greater than or equal to 2, right? Because it doesn't, a sub 1, for when n is 1, this is the rule. But for when n is either equal to 2 or greater than 2, then this is the rule. All right, let's see if we can write the recursion relation for the one down here, this arithmetic sequence. So we know that a sub n equals, so we start it, just exactly the same here. We can say a sub n equals, and what is it going to equal? Now it is the previous one plus 3. So how do we say the previous one? We say a to the n minus 1, right? Plus 3. So here we've defined it, but we need to, this works for all of them except for the first one. So let's say in this particular case that the initial index is 0. So then that would be the term a sub 0, right? So a of 0 is equal to what? Well, it starts at 12. So that tells us this tells us what the first term is. This tells us what every other term is. And so we can specify this. This is for all n, not n0, right? That n, when n is 0, this is the rule. But when n is 1 or greater, so n greater than or equal to 1, this is the rule. And that's a recurrence relation. And we can write these for all geometric and arithmetic sequences, right? They're just straight up because they recur, right? So we have to say what the initial one is. So we can say a sub 0 equals, and the very first start one is 9, so that's the rule for beginning it. And then we can say a sub n is equal to the previous one times 1/3. And we can put this in front or back. And here we're going to times it by the previous term, right? Which is a of n minus 1. Right? And now which ones are this for? We need to specify this is for all n that is greater than, not 0, right? It's greater than or equal to 1. And there we could write it for that one. And again, same thing down here. A of n equals, and what do we do here? It equals the a of n minus 1 minus 5. Right? But we're not complete. It's not completely defined yet because we have to know what that initial term is. So we need to know what a of, and again, the index could vary, right? Commonly there's 0 or 1, but so they could be anything. It could be what anything, but let's go ahead and say a sub a of 2. This one would start with the index of 2. Now let's stick with just really common ones. So let's do a of 1, and then we'll do, so this is for all n greater than or equal to 2, because a sub 1 is defined here, right? So a of 1 is equal to 4. And there we've completely defined those sequences using a recurrence, right? A recurrence relation.